We have some problem with the resolution, so some of the presentation will be cropped, but hopefully that should be okay to have a clear idea of what I'm doing. So the presentation mainly will cover what we have been doing in my group, which is a digital photogrammetry research group at the University of Calgary in the area of digital building model generation through diffusion of image and LiDAR data. So I'll talk quickly why we are interested in digital building models, what is the existing strategies, the methodologies, and some results and discussion throughout the presentation. And then finally, I'll talk about some current and future trends. And there actually, I'll try to make a link between the technology or new technologies that are available and some of the things that Dr. Abdullah mentioned in his talk. So why we are interested in digital building models? The UN actually usually every year tries to see where is the distribution of the population around the world. And by 2030, actually, it is estimated that 70% of the population will be living in urban areas. And just to give you an idea about what is happening, let's say locally in Canada, the Census Bureau did a study of the population growth between 1971 and 2001. So in metropolitan area, the growth actually in the population was roughly 45%. However, for rural area, the growth was 13%. And I don't think that's unique to Canada. I would say globally, that's usually the trend. We have more things going on in urban environments. So in order to have a controlled growth and avoid the social and environmental issues from uncontrolled urban growth, the decision makers should have good, accurate, current geospatial information to help them to make informed decisions. So when you look at urban environments, one can argue actually that the most important phenomena or features in urban environment is the buildings there. There are lots of applications like what we see here in the slides, like security application, military applications, telecommunication application. So the objective of this work is diffusion of image and LiDAR data in order to generate 3D models. So basically, we are accurate and realistic modeling and visualization of urban environments. So we can see actually the categories which we can use of the processing or data DBM generation strategies. We can see we classify them according to the sources we use, either it's image-based or laser-based or combination of both. The processing or the user interaction can be either manual, semi-automatic, or fully automatic. And finally, how you are going to produce your digital building model can be what we call model-driven. So in model-driven, you say, I assume my buildings are boxes. Or data-driven, where basically you let the data tell you what kind of buildings are you looking for. Or a mix between both, or what we call hybrid approaches. So in our research objectives, we were trying to say that we would like to be general enough to handle multi-source data. Hopefully, it should be fully automatic and hybrid approach between mix between data-driven and model-driven. So for us, actually, the digital building model generation, we can have it in two groups. First, detection of the building. Where are the buildings? Or making a hypothesis that I have a building in my sensory data. And the second part, which is the accurate modeling of the buildings. So for us, actually, LiDAR data is an excellent source for the detection or making hypotheses about the presence of building in our data. And then the image data will help us actually in deriving very accurate model parameters for the digital building models. So this is actually sort of a first part, the data-driven part. I'm not going to go through this, but I'll show you just some examples. So this is actually an image over the University of Calgary campus. And then this is the corresponding LiDAR data that covers the same area here. The color actually represents the height. So the brighter the color, that's the higher objects. So the first thing we do actually in our data processing is that for every point in the LiDAR point cloud, we classified whether it's part of planar surface or non-planar surface. So non-planar surfaces, for example, points in trees, bushes, some of the cars, and so forth. So in this graph here, what we see is the red points. These are the points part of planar surfaces, and the blue, those are the points which are part of rough or non-smooth surfaces. Then one of the important things we are doing in our group actually is what we call data characterization. because actually with LiDAR, you don't have a raster data, it's irregularly distributed data. So you have to look into actually how many points per square meters you have. So we estimate actually this point density. That might not be a big issue when you are dealing with airborne data. However, if you have low flying altitude systems or basically terrestrial systems, the data characterization will become important, and hopefully I'll go through this towards the end of my presentation. So then actually what we say that if we have neighboring points based on our estimation of the local point density that belong to planar surfaces, we group them together. So this is actually what you see in this graph here. So this is, for example, the dark gray, that's a ground. So you can see actually locally the ground is planar areas, and they are well connected. So you have actually the largest group is the ground. And then you can see the individual buildings are almost now starting to appear as clusters with unique colors. So then we do the segmentation process. Basically, we derive accurate representation of the model or the plane parameters for these areas. So we can see here that because the ground is not really a very smooth planar surface, you can see the ground is broken into different pieces. And then for each one of these segmented regions, we derive actually the boundary. So there are lots of techniques that gives you the inner and outer boundaries of the different areas. So at the end, actually, we say that what we say that based on the results of the segmentation, we classify each one of these groups either as planar, non-planar, whether they are ground or non-ground. And that's very important actually, because now that makes the building detection very simple process. So we can say actually, what is my hypothesis about the presence of a building in my data? We say if we have a planar region, which is not ground, which is significantly or considerably higher than the ground and has a certain area, most probably that's part of a rooftop of the building. So this is just show you actually some of the results here. So on the far left, you see the LiDAR point cloud. In the middle, you see actually the segmentation results. And at the right, you see actually the ground and non-ground objects. And then for these segmented features, we can see actually the segmentation of the different planes above ground. And in the middle, you see actually the boundaries of these areas. So the far right, actually, you see actually the detected boundaries from the LiDAR projected into the image. So let's look into this particular building here. So that's really the problem, or basically that's the advantage and disadvantage of LiDAR. LiDAR actually gives us a very good information about the more or less the overall shape of the building. However, because of the point density, in this case we have roughly 1.7 points per square meter, you can see that the boundaries of the buildings are not really clean enough that allows you to take this data and put it in a GIS database, for example. So we need to do some sort of regularization. So that's basically now the second part, which is the model-driven or the building modeling, how we can model these buildings and represent them with certain parameters. So there is actually, let's start with the simplest buildings. So the simplest buildings, they are rectangular buildings. So basically for us, the building can be represented as a box. So actually one of the nice ways to represent or regularize this, what is called the minimum bounding rectangle. So you take a boundary, you try to find the rectangle with the minimum area that includes this part. So then once you have actually the regularized part, it will not really nicely fit along the edges of the building. Then we can use the image, we project this rectangle into the image, we do some edge detection and then buffering of the edges in the areas we are interested in, and then we can do some sort of data processing to get the exact building boundaries. But now the problem, this is the simplest case. We have actually a rectangular building. So what will happen if we have a building which is more or less a little bit more complicated? Actually, what we developed, what we call recursive minimum bounding rectangle. And actually the idea is quite simple. So first we start by finding the minimum bounding rectangle for this area. And that gives us actually a rectangle. And then we track the boundaries and we see which points from the LiDAR boundaries are not overlapping with the MBR or the minimum bounding rectangle. And for each one of these chains, we do another level, or basically we project these points into the MBR, and then we have another level of MBR using the points and their projections, and we keep repeating this process actually until we inspect all the points along the LiDAR boundary. And then you can easily prove actually that the final shape is basically adding and subtracting these minimum bounding rectangles. So at the end, actually, we can have a regularized shape that follows the shape of the bell. However, when you put this into the LiDAR data, it will not fit, on the image data, it will not fit nicely. So if you do the edge detection, you have actually the final shape of the building, which is on the far right. So we did this actually for the University of Calgary campus. That's a digital building models which we generate. The only problem we have right now is that if we have buildings with funny shapes, it's not really a collection of rectangles, they will not be modeled. So this is actually the final product that we'd like to integrate the color information from the imagery with the positional information from LiDAR to have this 3D digital building model. So now let's see here. In the University of Calgary, which we would like to think it's sort of a representative, we say 75% of the buildings can be modeled with our approach. There are some other buildings can be partially modeled, like this one here, like these areas which are highlighted by the reds, cannot model by our approach, and this complex building we cannot use it, but we can do that semi-automatically. So the whole idea actually there that using this approach we can say at least 80% of our buildings can be generated automatically. So if I have just a couple of minutes, I will just say where we are going now or what can be done. So now if we are really interested in very large scale digital building models and also for indoor mapping. So I'll just give you an example of this digital building model in the University of Calgary. So one way of doing that you integrate multi-source data. So here I'm showing, for example, airborne data and terrestrial data. Both of them are laser scanner. And I would like to combine this data. So I'm not talking about solutions, but I'm talking about problems now. So the problem is that this is the airborne data. If you look at actually the terrestrial data, because it's much more accurate systems, very close to the building, you have very clean data that basically when you try to combine them together, you will see completely different characteristics. So that's why we call actually here, for example, this I'm showing the noise level in the airborne data and the terrestrial data, and also the variation in the point density. The airborne is very sparse data. The laser scanning on the ground gives us very dense data. So we have to do data characterization. You have to describe your data. And then you have to do the alignment of the data sets together. Yes. And then actually, at the end, actually here, what I'm showing is that the last or the far left two results, these are the results when you consider the point characterization, like the noise level and the point density distribution. The last thing which I would like to talk, and actually this is, I saw actually a very good link between this and what Dr. Abdullah was presenting, UAVs actually. So now we are talking about just image-based systems. So this particular system, which is Phantom DJ2, this is actually roughly $1,000, $1,500. So in this case, actually, we have only a camera system. The camera is what's called GoPro camera. You can tilt the camera to look down or look sideways. So this is actually, this is the processing workflow. And in this case, actually, we use what we call dense matching techniques, like the SGM. And we can have actually a very dense point cloud. But the problem here, because we are using a very low-cost camera, the camera here is a couple of $100, you have lots of distortions. You have to remove the distortions. So this is a result after the calibration. And this is actually the final point cloud. So here, actually, we are producing a point cloud for every pixel in the captured images. Here, we're talking about few million points. So this is actually just a 3D visualization, actually, of the point cloud we generated. And because it's coming from the imagery, you can easily actually have the X, Y, Z and the RGB values. So this is a very actually light system. I think it's more or less like 1 kilogram, the whole thing. You can actually do the autopilot. So you basically, whenever you are in an area, so as Dr. Abdullah was saying, that if you are traveling in an area, you don't really have the luxury of having a mobile mapping system moving with you. You can have this UAV. You can do your data collection very quickly. And then at the end, actually, you have a very good 3D model. And that ties actually to the 3D visualization and the realization of the data. So just to tell you how accurate this one here. So basically, we have the LiDAR data from the airborne system, which you see it here in red, and from the UAV, you see it in gray. So actually, the UAV data is much more accurate than the LiDAR. So, and the quality of fit between them is in the order of 7 centimeters. So this is actually my last slide, just to show you the difference between the airborne and the UAV base. This is actually the green points are the laser points, and the gray points or the color points, this is basically what we have from the UAV. So this is very actually new technology. It's very inexpensive, and it can produce actually very good products. So thank you very much.